Okay, geometry, we've spent the past few days talking about two-dimensional space and area. We did area of triangles, area of rectangles, area of strange shapes, area of shapes when the side lengths are irrational, scaling principle for area, and then we proved the area of a circle. How crazy was that? Well, now we need to get into three-dimensional space. All right, so while we get into three-dimensional space, let's talk about this three-dimensional right rectangular prism. Has dimensions 3 by 4 by 5. Let's determine the length of segment AC prime. Let me highlight that for us. AC prime. That line right there, it's going from the back left corner to the front right corner. So if we look at this shape, it is a triangle. So I'm going to continue this on here. So if we want the length of AC, we sort of need to figure out the length of, AC prime, we need to figure out the length of AC and use the Pythagorean Theorem because we have a right angle right here. Since this is a cube, I need another color. If I figure out the length of AC, not AC prime, right here, then I can use that to figure out the length of AC prime. So here we have a right angle. 3 squared plus 4 squared equals c squared. 9 plus 16 is 25. So c equals 5. Let's use that to figure out AC prime. So here our legs are 5 squared plus 5 squared equals AC squared, AC prime. This was AC, I should be clear. 25 plus 25 is 50. So AC prime is the square root of 50, right? If I simplify this, I can break it into 25 times 2. So AC prime is 2. 5 squared roots of 2. Okay, lots of right triangles, lots of right triangles in that right rectangular prism. Okay, let's follow up that quick little exercise with some questions to help review a bunch of ideas about points, lines, planes, three-dimensional space, etc. Okay, so follow the highlighter along. Would you guys say that line AB, which is right here, is parallel to A prime, B prime? Okay, why? Well, they're parallel because this is a right rectangular prism, so these are all right angles, and we learned that when something connects two lines, if a segment connected two lines and it connected at right angles, then the two lines would be considered parallel, right? So those are parallel. AB and A prime, B prime are both perpendicular to A prime and B prime. Therefore, they're parallel. Do AB, line AB, and line A prime, B prime lie in the same plane? Yes, they do. They lie in this plane. I can name this plane with any three letters, A, B prime, or any combination of those three letters. A prime, B, A prime, B prime, etc. They do lie in the same plane. Okay, how about we now consider line AC? I need AC right here. Consider line AC. Will it ever run into the top face? Will it ever hit this face up here? No, because this line lies in this plane, and this plane is parallel to this plane. So if this line lies in this plane, it will never connect that plane, right? Next one. Can you say the faces of the figure are parallel to each other? Well, no, not all of them are parallel. The opposing faces are parallel. Any opposing faces are parallel, but some of the faces are perpendicular to each other. So only the ones opposite each other are parallel. If any of the faces touch each other, they touch each other in a perpendicular fashion. Would you say that line B, B prime, right here, is perpendicular to the base? Yes, yes I would, because it's a right rectangular prism, so this line is perpendicular to that base and this base, or this top face. Is there any way we can draw another line through B that would also be perpendicular to the base? Well, no, we can't do that, because any line through B that's perpendicular to this base is line B, B prime. Okay? I mean, here's my base. To draw a line perpendicular to this base through this point is that line. There's only one way to make a perpendicular line through a plane. What's the distance between the top face and the bottom face? So I've got the top face and the bottom face. What's the distance? Well, the measurement of this segment, or this segment, or this segment, 5, or that segment. That's the distance from one to the other. Do lines AB, right here, and B prime, C prime, AB, and B prime, C prime, meet? Ever? No. Well, are they parallel then? This line and that line? If I highlighted them, it'd be this line. Not what I was looking for. This line and that line. They are not parallel. They will never meet. They are actually skewed. They are considered skew. Can AB and, sorry, I lost my train of thought. AB and B prime, C prime line the same plane. So AB and B prime, C prime line the same plane. No, that's the definition of skew. Name a line that intersects plane A, B, B prime, A prime. Name a line that intersects this plane. Well, that line, that line, that line, that line, or even that line, they all intersect that plane. It's very easy for a line to intersect a plane. Name a line that will not intersect a plane. So this plane, well, this line won't intersect it because it's parallel to it. That line, and that's really it. Oh, this line, it's skew to the plane. Or no, parallel. Yep. Sort of fun. All right, let's move on to a summary of properties of points, lines, and planes. Okay? So what we're going to see now is a bunch of properties and diagrams. You're going to need to draw these diagrams in to the best of your ability. I would grab a straight edge and get them going. If you draw them well, it'll help you understand them. So here we have 2 points, P and Q. They determine a distance, PQ, a line segment, PQ, a ray, PQ, a vector, PQ, and a line, PQ. So I drew a line, I labeled it PQ. Notice the arrows on both ends. Here we have 3 non-collinear points, A, B, and C. They determine a plane ABC, and in that plane they determine a triangle ABC. So I drew a triangle on the plane and labeled it ABC. Cool. Here we have 2 lines either meet in a single point or they do not meet. Lines that do not meet and lie in a plane are called parallel. Skew lines are lines that do not meet and are not parallel. So I have 2 lines that meet at a single point, 2 lines that never meet because they're parallel, and then a pair of skew lines. So this line, let's highlight it. I've got this line and that line are skewed. That's why I've got this one dot dot coming out and this one. Those lines never meet. They are not parallel. They are not perpendicular. They are skewed. Give a line L and a point not on L. There is a unique line through the point that is parallel to L. So on your page you'll see this was already written there. Well, I drew another line through this point. They're just parallel. There's only one line through that point that's parallel to L. Given a line L and a plane P, then L lies in P, L meets P in a single point, or L does not meet P, in which case we say L is parallel to P. So in this first case, I have a line that is on plane P. It lies in plane P. Here I have a line that goes through plane P at one point. And here I have a line that is not on the plane. It's therefore parallel to the plane. Two planes either meet in a line or they do not meet, in which case they are parallel. So here, the first A, I have two planes that meet in a line, and part B, I have two planes that do not meet and therefore are parallel. Two rays with the same vertex form an angle. The angle lies in a plane and can be measured by degrees. That's what I drew. Two lines are perpendicular if they meet, and any of the angles formed between the lines is a right angle. Two segments or rays are perpendicular if the lines containing them are perpendicular lines. So this first example, I have two lines are perpendicular. Here I have, the second example, I have two segments or rays are perpendicular. And I guess I should have put arrowheads on the ends, because if those rays or segments are perpendicular, then the lines containing them are perpendicular. Number 9, a line is perpendicular to a plane if they meet in a single point. And the plane contains two lines that are perpendicular to L, in which case every line in plane P that meets L is perpendicular to L. A segment or ray that is perpendicular to a plane if the line is determined by the ray or segment is perpendicular to the plane. Lots of words in that one. So I have an example of a line that is perpendicular to the plane right there. Draw several lines that lie in the plane that pass through the point where the perpendicular line intersects the plane. So I just drew a bunch of lines. This one is perpendicular. The rest of them lie in the plane. And that got really messy. Two planes perpendicular to the same line are parallel. So that's why, oh gosh, we see there, sorry about that, they're perpendicular to each plane. This line is. Therefore, the planes are parallel. Two lines perpendicular to the same plane are parallel. Any two line segments connecting parallel planes have the same length. So AB is congruent to CD. The distance between a point and a plane is the length of the perpendicular segment from the point to the plane. It's the shortest distance from a point to a plane is a segment perpendicular to the plane. And that's it. That's our lesson summary. Okay. We have lots of properties. So we went through properties 1 through 12. Okay. We need to be able to know what we're looking at. All right. And you guys can. So we'll go through the problem set tomorrow and clear up any questions or concerns that you may have. But we'll have to read some three-dimensional pictures, which can be challenging, but I know you guys can do it. Good job today.